This is February-March 2026, paper 1-2. The first question is ratio of kilometers to nanometers. The best way about this would be to just put this on the calculator with prefixes and you'll be good to go. So if you put this on the calculator, you'll get your answer as 1 into 10 to the power 12. And if you want me to show this to you, then use a fraction symbol, put 1 exponent 3, come down to the denominator, and then write down 1 exponent minus 3, press equals to, and you can see that it's going to show you what that power should be. So it's going to be option D. Question 2, what could reduce the systematic errors? Now, systematic errors deals with if it's about a graph, it's a false origin. It could be because of zero errors due to instruments, and basically dealing with instrumentation control and process. So averaging a large number actually reduces the random error. So this is what we do for random errors. Careful calibration, yes, so that we can get rid of zero errors. Reducing sample size, this is irrelevant, doesn't do anything. Repeating the experiment again reduces random errors because repeating and averaging is going to reduce random errors. So the best answer for this option should be option B. Question 3, student measures the current so-and-so. He wants you to find the percent uncertainty in the value of resistance. So we start with V equals to IR and make R the subject of the formula. This is going to be V over I. So using the divided by percentage uncertainty formula, this is going to come down to delta V by V plus delta I over I. This is the error function for delta R by R, and this is what we need for percentage uncertainty. So we're just going to add these errors. So this is delta V and this is delta I, and put this into this equation. So we get 0.01 divided by 50 plus for current, and potential difference is 0.1 divided by 500. And then we multiply the whole bracket with 100. So our answer for percentage uncertainty is going to come out as 0.04%, which is going to be option D. Question 4 says graphs can be used to represent motion of an object where relationship in quantity is representing the property. Now, we understand that for every graph, there are two things we can check very quickly. First is what the area going to represent, and the second one is what the gradient represents. So we're just going to match their attributes to the respective graph. So the first one is the acceleration is area. Acceleration is never the area of anything. And then the acceleration is the gradient, looks like it, of the velocity. Yes, that's correct. Displacement is the gradient of the velocity. No, that is incorrect. It's actually the area. For if it was a velocity diagram, then that would be the area. But option D, velocity is the area under the displacement. This is a false question. There is no question for displacement or area under the displacement time graph. So the best answer for this situation should be option B. Question 5 deals with the water surface. Now, this question was already repeated in 2022. Paper 1, if you want to check this question out, then please be my guest. You will see the same question over there. Now, the question is about the time interval between the person dropping the stone and hearing it, the water. So, for example, if this is the cliff where the person is standing, they throw the ball, the time is ticking, the time is falling down, the ball keeps falling down, and then when it hits the water, there is a sound wave going up that the person is going to hear. So the time interval is required for this difference. So first, time to fall down, let's call this TF, and then time to go up, let's call this T up. Now, if you mess up the calculation at the end, you will end up getting option A, but that's the incorrect answer. But let's see how to solve this question. So we're going to use the equation of motion to calculate the time for fall. S equals to UT plus half GT square. This is going to naturally become 0 because we're leaving it from rest. So displacement is given to us as 78 meters, that is 78 meters tall, equals 0 plus 1 over 2 into the gravitational acceleration definitely is 9.81 and into t squared. Don't forget that this is a square that goes to the side, takes the under root. Your final answer will come out as 3.98777 seconds. Now, this is the time to go down. We're going to use the same distance, same height, to calculate the time for the sound wave to travel to go back up again. So the time for the sound wave to go up will simply be speed equals distance over time. Speed is given to you as 330. So the distance is still 78 meters going upward. This is T up. Time to go up is going to come out as 0.23636 and so on, recurring decimal place. Now, if you mess up the calculation and the idea, you will accidentally subtract this time with this time. And if you do that, your answer comes out as option A. Now notice how the examiner has set traps for you for your miscalculation or misunderstanding of the question. The question is about the total time interval So we're going to add these numbers together, which is going to get you an answer of option D, 4.22 seconds. Question number 6, a toy moves in a straight line. Some sections of times are given with reference to displacement. Now please note that the displacement time graph, the gradient actually represents the speed. And what happens to speed, we can also comment about the acceleration. That is particularly required for this question because we're going to describe forces. So force is equal to mass into acceleration. If there is an acceleration, then there will be a resultant force, either forward force being greater than backward force, or backward force being greater than the forward force. There's something going to be around the resultant forces. So let's see how this is going to go. He says, in which system the car is in equilibrium? Equilibrium suggests that the acceleration is supposed to be zero. All the forces acting on the system should cancel out and we have no acceleration whatsoever. So we're going to find out areas in the graph where the speed at least is either constant, concluding that there is no acceleration, or there is no speed at all. So in the first section from 0 to this section, what's happening at t1, the object is not moving at all. So if the object was on the ground, whatever its weight was, the normal reaction force would be equal to this. So the system is still in equilibrium. So T1 is in equilibrium. In T2, the constant gradient suggests that the speed is constant. If the speed is constant, then the acceleration is zero. If the acceleration is zero, then F equals to ma. The force will also be zero. The resultant of all the forces will also be zero. So T2 is also in equilibrium. Same case with T3, because T3 looks like T1. In this section, the object is not moving. If it's not moving, all the acting forces are still balanced. It is in equilibrium. And in T4, the object is trying to slow down, or you can say it's trying to go back where it came from. Since the gradient is constant, the speed is constant. If the speed is constant, the acceleration is again zero. If the acceleration is zero, the resultant forces are zero, and the system is in equilibrium. Again, it could be that due to the forward forces, backward forces, whatever is happening with the forward and backward forces, the final answer is yielding zero acceleration, which means the system is in equilibrium according to first and second laws. So the answer will be option A, the time interval for across all the board. At all these timestamps, the system is in equilibrium. Question number 7 has been a repeated question, has been a repeated occurrence. He wants you to understand that there is a clockwise movement, the radius is 12 meters. The 4 seconds to move from P to Q. So from P to Q, it has a time frame of 4 seconds. The average velocity. This question is old and has been asked many times in different formats. Now, since we are interested in the average velocity, we will find the formula as total displacement divided by total time. So the time taken or time given for the question or situation is 4. But what about the total displacement? Displacement is the shortest path, so it should be P to Q like this. Although it's going to be moving like this, probably, or if it is moving in this direction, then it is going to go like this. But for displacement, it doesn't care about the direction or it doesn't care about the way that distance is covered, but it does care about the specific direction. So it's still going to be P to Q, which looks like the hypotenuse of a triangle. This is 12, this is 12. So if you want to find this, it would have been displacement PQ equals to 12 squared plus 12 squared under root. Now when you do that, your answer will be 16.97. When you divide it with 4, your answer comes out as 4.24 meters per second, which is going to be option A. Now we move to question number 8. Question number 8 is, a person is suspended from rope vertically below the helicopter. The helicopter and the person stationary is the key word above the ground, which means that all the acting forces are equal and balanced. What forms the Newton's third law pair with the weight of the person? So if only the person is involved and we're only interested in the weight of the person, then this weight is being created by the earth. So the next thing that the pair is going to complete with is the force on the earth by the person. That's going to complete the Newton's third law pair. So let's first eliminate all the options in which there is no discussion of the person itself. So person is discussed, we will consider this, but consider this. Gravitational force applied by the earth, no discussion. Helicopter, no discussion. So let's check option A and B on its own merits. The upthrust, not possible, because even if there was an upthrust, it was going to be because of the air, which is going to be rho GV, which is going to be very, very small because the density of air is very small. So And definitely the force of tension in the rope on the person looks like it. But again, we cannot accept this because it's not the tension. Tension involves the rope. So let's check the options again. The gravitational force, okay, force applied by the person on the earth, that looks like a good option. Force applied by the person on the helicopter, no. Then again, this is going to be a representation of tension. So the best answer for this option is going to be option C. So what's happening here is that the person is being attracted by the earth. That becomes a W. And the person's gravitational field is also attracting the earth towards itself. That is also going to be the weight. This makes the Newton's third law appear, and this is one of the common misconceptions that sometimes is going to be asked. But this is the answer for the question, is option C. Question 9. Two small moving particles collide. After collision, the particles move different directions. What is essential for the momentum to be conserved in the collision? So, no external force acting in the system. That's true. Should be true. No kinetic energy. This is not necessary. Even if it is, even if it does, it is not conserved. The collision is still elastic. It could be elastic or inelastic. It is still going to conserve momentum in both situations. The collision is inelastic. It is false. The relative speed of approach is equal to the relative speed of separation. Again, this is a special case for elastic collision. So this is not necessary to be required. But with the condition that is always going to be true, it has to be true for the sake of momentum at least, is the external force. There is no external force acting, and this only the objects that are interacting with each other by any means necessary. You'll find question number 10 interesting. You will find something repeated in October-November 2008 paper 1. You will also find these questions in Mathematics Mechanics 1 paper in the chapter of forces and dynamics. So we're going to try to solve this question by physics and then by applying some mathematics to it. Let's see how this is going to go. So block 1 has a mass of 3 kg. I'm going to write this down, 3 kg, and block 1 has 1 kg mass. The rope is over frictionless pulley. There is no involvement of friction. Block 2 has a mass of 1 kg suspended as shown. We have already written that down. It says that the blocks accelerate when they're going to start to move. The acceleration of free fall is g. The unit of g is meters per second square. The tension in the rope in newtons is newtons. Find the tension in the rope. Now, the first things first, let's find the acceleration first, because only then we can find out the force. So for the acceleration, the idea is the resultant force system. So let's consider all the acting forces on the system. There is only weight that is downwards. The block 1 is in contact with the surface, so there should be some friction, but since it says there is no friction, there is no one stopping it. So the resultant force equals to being mass into acceleration actually comes down to the mg minus no friction equals mass of block 1 plus mass of block 2 into acceleration. Now, since we know that the mass, this is what is causing the system to move, this is value 1, so this is only g. There is no friction, friction is 0, so this gets eliminated. And then we have 1 kg with 3 kg being added together. So this is going to be 1 plus 3 into the acceleration of the system. So acceleration of the system is actually g divided by 4. If we let go of this, it will actually be moving at 9.81 divided by 4. Now, this is going to feed us into the next situation. We're going to use a bit of mathematics here. So I can solve this question by two methods. I can just look at block 1 or I can just look at block 2. If I consider only block 1, then what is happening here? You see, block 1 doesn't know what is connected on the other side. All it knows is there is a rope that is going to try to pull it with the force of tension. Similarly, block 2 does not know what is holding it back. So there is again a force of tension in the opposite direction, which is of course a representation of friction elements, resistance, drag, whatnot, or the inertia of block 1. So let's figure this out in reference to block 1. So for block 1, the pulling force is actually the tension. All it knows is T. So if I apply this into F equals to ma, this is going to be T minus no friction in the system. So that's 0 equals mass of the own system, which is 3 kg into A. So T becomes equal to 3A, and we know that A was G by 4. So this becomes G by 4. So tension should be equal to 3G by 4. Now this is what we did for block 1. Let's consider block 2 and its life. So block 2 thinks that there is weight downwards. So with reference to block 2, this will be the pulling force, which is according to F equals to ma. This is going to be mg minus tension, right? Equals to mass of the own system, which is again 1 kg. This is 1 into acceleration, which is g by 4. of the system. So since we want to find tension, tension comes to the other side. This comes here. So mg only becomes g because this m was 1. This is 1 kg. So g minus this one to the side, this is g by 4 equals t. T comes out as 3g by 4 again. So tension in this case is option C. I've shown you two methods to solve this. The first method to find acceleration is going to remain fixed. Then you can use either block 1 or block 2's life to find what the tension should be. Question number 11 is straightforward. He says, determined by the relationship of the physical quantities, mass is supposed to be determined. Which relationship always is equal to the mass of the object? So resultant force, which is F divided by A, yes, this is definitely equal to mass. Linear momentum divided by velocity, yes, this is also equals to mass because momentum is mv and resultant force is ma. Weight of the object, which is W divided by the acceleration of the object. Now, this is incorrect. This cannot be true. You see, if, for example, there is a system in which the weight is the pulling force, like say, for example, in this case, the weight was the pulling force. Was it equal to the acceleration of the system? It wasn't. So we have to be careful about the understanding of F equals to ma. This F is because of all the pulling and stopping forces. This acceleration is because of these forces. What acceleration is going to be caused in the whole system? There are two sides of the equation, so no, acceleration of the object is not gravitational acceleration. If this had been W divided by gravitational acceleration, then definitely this would have been mass. So the first two equations give us mass, but the third one does not. It is a misconception, but I definitely see what the examiner has set a trap for you. But we understand that this is not true for this. There should be some involvement of gravity in that sense. Only then we could have chosen option 3 too. So correct answer will be option B. We move to question number 12. This is a good question. It's a 2D question turned into one-dimensional question. So the question is that a block of 2m is being thrown into the block on the basket below. It must have some velocity while falling down, but we are not interested in that because we're only interested in the velocity in this direction. So whatever it may have, this is there to cause confusion, but there is nothing very confusing about this. It's a very straightforward question. Let's see. So momentum before this was dropped in and should be equal to momentum after this was dropped in. So the momentum before is capital M into 30 centimeters per second. And what happened after this? When this was dropped inside, then the total mass became 2m plus m. New velocity v, we don't know. You can notice that this becomes 30m equals to 3m into v. We want to find out. So m cancels out. 3 causes this 30 to become 10. So v should be equal to 10 centimeters per second, which is going to be option A. Now, be careful about this question. They have been started repeating many times, so we can be careful about this and just ignore the 2D perspective. So, two children are balanced horizontally in an equilibrium plank. He wants us to find the ratio of x and y. So, before we begin the question, we just simply need to find out the moment about the pivot. So simply the moment would be the anti-clockwise by child x and clockwise by child y. So since these are masses, I need the forces to be causing moment. So I know that mass can be converted to a force by mg, by weight. So the left-hand side, which is child x, should be equal to child y in terms of their moments. So this will simply be 20 multiplied by g multiplied by its distance from the pivot, which is x, equals to child y. There was a mass of 15 into g into its own distance from the pivot is y. Now we can very clearly see that g is going to get cancelled out, and since we want the ratio to be x divided by y, I'm going to bring y to the other side and 20 to the other side. So this becomes x over y equals to 15 divided by 20, which leads to 0.75 being my answer, which is option C. Question 14 has been repeated in February-March 2023 series, exactly 100% copied. So this is an interesting question in terms of your own understanding of vector components, your own understanding of how sine and cosine actually angles work from 0 to 90 or 0 to 180. It's not just going to be about memorization. It's actually going to be about true understanding of vector components. So let's see what the question is trying to say. So he's saying what's the relationship between R1 and R2. Now, first things first, since the painting is identical, they mentioned somewhere here, same picture, so we can assume that the mg is actually the same. this R1 is actually completely against the mg of the picture. So no matter what the string is going to look like, the value of mg is going to remain the same. The value of R2 will also remain the same. So the first conclusion, because mg is the same for both paintings, it should be equal to R1, which should be equal to R2. So my first relationship is going to help me eliminate option C and option D. It's not possible. There's going to be R1 equal to R2, that's for sure. Now, we're confused about T1 and T2. Now, surely, if you use a basic idea, the tensions in both strings should be different. So most likely you should have selected this part, even if you weren't able to solve this, but we're going to solve this by a logical method and see what happens. So, for example, if we were to draw a straight dotted line here to find out the vector components, let me call this as the angle X and let me call this as angle Y. And we understand that angle Y is greater than angle X, at least visually speaking, it's greater. This diagram. So see, the horizontal components of these components will not make any difference, or will not be important for the solving of the question, because it doesn't matter, because they're going to be cancelled out in both cases. So really, it all comes down to the vertical components, what the vertical component is going to do for us, because R1 is in the upward direction, so mg is going to be split by T1 and T2, right? So let's say that the tension is equal in both strands. So this will simply be two components which are pointing downwards. So in this case, if it is pointing downwards, let's say like this one, the component should be T1 sine of x and plus T2 sine of x should be equal to R1. Now, since we understand that T1 and T2 are exactly the same, so we can write down T2t into sine of x equals to R1. Now here, we can develop the same strategy here, because there are two components. They're going to be two arrows pointing downwards with angle y this time. So this will simply be 2t sine of y angle equals to R2. And we understand that they're both exactly the same. So it doesn't matter if I write down R1 or R2, they're going to be exactly the same. We've established that at the very beginning. So let's make both the subject of the formula. Let's make T1 the subject of the formula and T2 the subject of the formula. For diagram 1 and diagram 2, right? Sorry, this is not T2, this is still T1, is given us in the question. This is still T2. Anyways, so let's say that this is T1 equals, this becomes R1 divided by 2 sine of x, and this is T2 equals to R2 divided by 2 sine of y. We understand that these r's are exactly mg, so they don't get involved in the comparison. So, and 2 is also a constant, so I'm going to eliminate this. So I get T1 is actually proportional to 1 over sine of x, and T2 is equal to 1 over sine of y. Now, if it still doesn't make sense to you, you can use assumed values here and be done with it. So for example, this could have been 30 degrees and this could have been 50 degrees. This could have been 60 degrees, something more than x. And you could have seen what is happening. So I mentioned this at the very beginning, that y is greater than x. And since I can see that they are not 90, this is not 90 degrees, because sine or sine function actually increases up to the angle of 90 degrees, and at 90 it gets a value of 1. So most likely your answer will be between 0 and 1. Now, I understand that if y angle is greater, its sine value will also be greater. So since y is greater than x, this value will be higher, and this T2 will be smaller, because in the numerator they have the same value, mg. So that becomes the decider. And since the angle x is smaller than y, this will have a smaller answer as compared to the rest of the equation, as compared to T2. T1 will be slightly larger than T2. So naturally, I come to this conclusion that T1 must always be greater than T2. You could have compared this by using, for example, the division method, like T1 divided by T2 is equal to sine of y divided by sine of x, because they're all inverses. So after setting up the reciprocal, we will see that the T2's component comes here and T1's component comes here. And since y is greater and x is smaller, this ratio has to produce an answer greater than 1 and can only happen when t1 is greater than t2. So there are multiple ways to look at this and visualize this. The answer should be t1 greater than t2, which is option B. The reason I've taken more time to this is because I've seen some other explanations online which are not diving into the fact that this is more visual than an understanding or then something that is supposed to be memorized. No, there is an understanding. There are values behind the question, and that's how you're supposed to think about this. I understand it's difficult, but since now we know how to solve this question, we can take this up into our knowledge bank and increase our understanding. Question 15 was very straightforward and simple. It's asking about the greatest pressure on the top of the surface, but since this is water, that is rho g h. H is depth. Depth always goes from top to bottom. So wherever we will find the greatest depth, we will consider the greatest pressure, which is going to be option C. Very straightforward question. No questions asked, nothing required. So now we move to question number 16. Question number 16 just requires a bit of algebra. He wants you to find the same density objects. So let's find the density of object M. This is mass M. Mass divided by volume, which is going to be x. This is going to become x cube. Density of this object will become 4m divided by x 2x, 2 cube, and density of r is m divided by the volume. So since it's a cylinder, this will be pi r square h. This will require a bit of algebra. So this is pi. R square is x squared, and h is height, which is x over pi. So this is x over pi. You can see that pi cancels out. We're left with density of r to be equal to m divided by x cubed. So it's similar to p. So p and r are going to have same density, but it's going to be option C. Question number 17 has been repeated in these parts. I would advise you to go check out these questions. These both belong to paper 2 questions. I mentioned the question numbers and year and variance. I would highly appreciate if you try these questions out and see what the marking scheme says and try to teach this part to yourself. All right, he says that at x, it already has a kinetic energy of 8 joules. And when it reaches y, it now has kinetic energy of 3.5 joules. What happened to the rest of the energy? So as the object was gaining height vertically, it was investing this 8.5 energy into gravitational potential energy. So out of that 8.5, 3.5 still it has in form of kinetic energy. The rest of it must have converted into gravitational potential because the air resistance is negligible. There have been no losses in the system. So I would argue that the energy available in the system before everything began was 8 joules. Energy still available, still present in the system in the form of kinetic energy 3.5. So what is the energy that we can't figure out where it went? That must have been converted in gravitational potential energy. So change in kinetic energy must be invested in gravitational potential energy. This is where we get the formula, which is going to be 8 minus 3.5 equals, or you can simply add the subtraction here and take that energy as mgh. So he's given us, he hasn't given us the mass. We were supposed to find the mass. So m into 9.81 into the height gained against gravitational attraction is 8.8. So the mass in this question comes out as 0.0521 kg, which should be option B. Yeah, that's right. Then we have question number 19. It says that the speed of the object increased from 10 to 20. In this situation, we will label that energy as E. And when it increases from 70 to 80, what is the change in terms of E? So let's figure out what the value is going to be in this situation. So the mass is not changing, nothing else is changing. We have half mv squared. Now, since it's about the change or increase, we can say that this will be half m into 20 squared minus 10 squared. If we calculate this and we have made this to be E, this is going to come out as 300. But we're not going to go into that method. Since if I'm going to compare this energy with the new situation, and I am comparing with half m 80 squared minus 70 squared with the new energy E dash, then why not flip this? Because I want this to be found out, or you can just simply use this one. So half m cancels out. We're doing the comparison. And when you put this in the calculator, you will find out that the answer is going to come out as 5e. So you could have done this way, the E dash, new energy, divided by E, which we have labeled as 20 to 10, 20 to 10 square, 10 square to 20 square is E. So this is going to be 80 squared minus 70 squared divided by 20 squared minus 10 squared. E goes there, and you get your answer. Now be advised that you might, apologies, I missed on question number 18. I'll get back to this later. So you might do this problem. You might look at this problem as, for example, you might think that 80 minus 70 square, because it is V square, may give you the right answer. This is the only problem that I've seen students struggle with. It's not whole square, it's a square of speeds. And definitely we understand that by mathematics that, let me write that down here, that A plus O minus B whole square is never equal to A square plus B square. It's not equal to that. You can check this on the calculator. Check this, for example, 80 minus 70 squared, and then 20 minus 10 squared. They'll give you the same answer because that's also 10 squared, that's also 10 squared. You will not be able to see the change. But we understand that since kinetic energy of half mv squared, when the energy is already operating, when the object is already at 80 meters per second square, it is miles ahead, at least as compared to 20 square. So be careful. It shouldn't be that way, right? So the answer of this question will be option C. When you find this, it's C. Let's go back to 18 that I missed. This is again based on a simple mathematics question, which is power equals to force into velocity. He's asking you about the velocity of the object. So V is equal to P divided by F, which should be option C. The tricky part of the question is that it's so simple and straightforward. All right, then we get to question number 20. Question number 20 requires a bit of analysis, you can say, because there are a lot of variables that need to be manipulated. Now, let's say this is the power station, and this is its useful output, and this is its total input. First thing that you need to do is make sure that everything is in the same unit. Because you're going to be working with watts and joules, please note that there is some value given for time. We can convert power into energy by using this equation. We can interchange them. So what I'm going to do right now is I'm going to stay in watts, or you can stay in energy. Let's stay in energy. Okay, let's try that one. So he says the average power output of the system is watts, which is joules per second, as P. So this is the power output of the system. And if I multiply time with it, this becomes in energy. This is joules output. Now, what is the input of the system? The input of the system is determined by how much coal is being brought in. So energy of 1 kg of coal, mass of coal, how much is available, and how many trains are coming in. So if you multiply these three quantities together as M into N into E, your answer still comes out as joules. So these are the joules of energy that you're putting in as chemical potential, and this is the amount of joules you're getting out as electrical energy. So since the expression of efficiency is useful output, which is PS, divided by the total energy input, which is MNE, this should be option A. Yeah. And even if, for example, you had tried this by using the logic of just watts. This was joules, and if you divide this with S, this will whole divided by S, and then will go again in the numerator as PS. So you can keep the whole question in joules, or you can keep the whole question in watts. Be careful about that. Question number 21 is again based on memory, very straightforward question. Object undergoing elastic and plastic deformations. What happens to them? So they are not permanently deformed, not permanently deformed. They are permanently deformed, are permanently deformed. So the most common option is option D, very straightforward question. Saves a lot of time. Let's move on to question number 22. This is from Young modulus. So Young modulus is FL over AE. So F is staying there, L is staying there, D is going to cause trouble. A and extension is also staying there. So A is going to cause trouble. It's a diameter problem. So Young modulus is equal to FL over cross-section area will be pi D squared by 4 into E. This 4 goes up. This becomes F4FL divided by pi D squared E. So the best answer should be having a 4 in the numerator and pi D squared E. Yeah, this will be the option. And this is going to be a common question. They give you diameter and then ask you about the cross-sectional area, how that's going to change, so on and so forth. So just be careful about this. And how we got this d squared by 4 is simply because this is cross-sectional area. Cross-sectional area is actually pi r squared. Now, since only the diameter is given to us, so this will be pi into d divided by 2 squared. And this becomes pi d squared divided by 4. That's why I use this trick quickly to save time. Then we have question number 23. It's interesting. You can read the question, the whole situation, whole scenario is given to you. I'm just going to go to the answer directly and see what happens. You see, the system is already here. Somebody's holding it there. And when they release it, the object goes down and goes up 4 centimeters down. We can say that when it goes down, the Earth's gravitational potential energy is invested into the system. Somebody gave it that energy. So let's figure out what's happening in this situation. So energy simply given into the box is going to be mgh, which is 4 centimeter loss of gravitational potential. So this is going to be simply 8. mg is already given to you. Into h is going to be 4 into 10 raised to the power minus 2 centimeters. This is going to come out as 0.32 joules. This was the energy as the object fell down. The Earth attracted it, and now that energy is present inside the box. Now, when it's only in the box, the spring stretches back up again, goes up. Now, just imagine that this energy, because it fell down from this to this location, gravity has given that energy to the box, and the box has given it to the spring. So today, the elastic potential energy in the spring, because previously it was unstretched. Now, the elastic potential energy is again 0.32 joules. All the energy by the gravitational has now been invested into the spring. The spring has it now. Now, the spring tries to bring the object back up again to a certain height, which is 2 centimeters away. So what happened to this energy? This energy went into 2 places. First, since it is still stretched and hasn't returned back to the position x, there is some energy still retained by the elastic potential energy in the spring because it is still 2 centimeters below the starting point. And some of the energy was used back to gain that height back by the box to go up, because it was at 4 centimeters, now it has gone up. So it took away some gravitational potential energy from the elastic potential energy available in the spring. So what is the current elastic potential energy when it is at this position? It will be found by half fx. So 1 over 2, force is 8. The distance moved by the spring, or still has in the spring, is 2 centimeters. 2 into 10 is, this comes out as, let me find this out for you. This comes out as 0.08 joules. It's still present in the spring. Okay. Now, what's the gravitational potential energy at this location? Because it was given to the box gave it to the spring to stretch, and now the box still has it to go up, used it to go up. So today the mgh will be 8 into this 2 centimeters, again minus 2. This is going to come out as 0.16 joules. So the idea is, whatever the spring had at the beginning, the spring had 0.32 joules. After many oscillations, when everything has settled down, what has successfully been recovered? What energy is still present in the system? So since the spring is stretched, it contains 0.08 joules of energy today. So the whole system started with 0.32 joules of energy. Spring has 0.08 joules of energy, and the gravitational potential energy, although by falling down gave that energy to the box, has demanded some portion of it back. Only then the box went up, and that portion demanded back is represented as 0.16 as mgh. So the system started with 0.32, spring has 0.08, the box has 0.16 because it is at a certain height as reference to the Earth. So how much energy are we still left with which is not accounted for, that we can't find in the system? When you subtract 0.32 from 0.08 and 0.016, you get 0.08 joules. So your final answer comes out as option B. 0.08 is the energy lost from the system, which is still unaccounted for. The spring has some energy, the box has some gravitational potential energy, which it took back, which it brought back or asked for it back to go back to position O or X at this point. So question 24, frequency is this. We're going to use V equals to F lambda. If you're good at this, you must have memorized the whole spectrum. But if there is a problem, you can use this trick and method to actually get very close to your understanding if you still remember something. So lambda is going to come out as 910 nanometers. Now, for this to work, you need to remember that red is 700 nanometers and violet is 400 nanometers. Now, since this is greater than red, it means it's going to be infrared or micro or radio, at least. For example, we're going to reject violet and ultraviolet, X-ray and gamma ray. That's not possible. So X-ray and ultraviolet are rejected. Visible light ends. The greatest possible wavelength is 700. So visible light is also rejected. We're going to come down to infrared. So if you hadn't remembered anything, you could have still at least tried to do this. But even for this, you need to remember that wavelength of red and violet are supposed to be memorized. Question number 25. A string stretched on a string to vibrate, which means it's going to be a stationary wave which is fixed between 2 points. There is a string plucked from a certain point and it's going to cause a stationary wave to be set up. So the first thing we need to fix is it is a stationary wave, it's not a progressive wave. What about the particle is correct? So he says there's no point checking this statement, there's no point checking this statement. P and Q vibrate with a phase difference of 90. This is incorrect. Phase difference of Q and R, yes, this is true. You see the phase difference between P and Q is 0 degrees. P and R is 180 degrees. And Q and R is also 180 degrees. And even if, for example, there was one particle here and one particle here, just crossing the boundary, this is X and this is Y, they will still have a phase difference of 180. So that's special about the stationary wave, that the phase difference between particles after they cross a node becomes 180, straight head on. And if they're on the same side of the wave, then there's no phase difference between them. Is going to be option D. That's a good question. Question number 26. What describes the displacement of the particle of the wave? This is again based on memory. The distance in a specific direction, yes. Distance moves per direction per unit time has nothing to do with the answer. Maximum displacement is usually called amplitude and it could be in both directions. The product of speed and wave, now that is V equals to F lambda, or product of speed and wave time. Still doesn't make any sense. Yeah, wave time, yeah. So this will be V is equal to 1 over T into lambda, T multiplied. This is wavelength. So this is again incorrect. So the best answer would be option A, because C is giving us the value for amplitude from its equilibrium position. And displacement needs to be in a specific direction, either positive or negative. So the best answer that fits the description is option A, according to definition. Question 27, he says, this is about Malice's law that has been added in your course since 2021. It says the transmission angle filter vertically polarized. So this is the plane of the wave. Between the plane of the wave and plane of the filter, that is going to be the angle of 60. And then it is taken to 90. So after crossing the first filter, the wave is not like this, rather it's like this. So when the wave is coming in like this, slightly at angle, the difference between this wave and this one is today going to be 30 degrees, because from 60 to next 90, as shown by the examiner, there's a gap of 30. The transmitted light is required. So this is a two filtration system. This input becomes the output here. This output becomes the input here, and the input then becomes the output here. So what I'm going to do is I'm going to solve this in a single go, because they're successfully becoming the inputs to the next filter. So the transmitted, let's call this IT, should be equal to I naught, which is introduced here probably, yeah, into two filtration systems, which is going to be cosine square of first filter multiplied by cosine square of the second filter. So when you solve this, this is going to come out as 0.1875 I naught, which is going to become 0.19. This question has been repeated many times, so be careful about this. You see, the idea is we take the angle between the plane of the wave and the current orientation of the system. First, the wave was vertically planed, so based on this, the filters were placed like this at an angle of 60. So this angle between the wave plane and filter plane was 60. So we took cos 60. But next, when the wave was polarized, that not only just changes the amplitude, it also changes the orientation of the wave. Now this is moving like this. Now between the plane of the wave and the plane of the filtered current position, there is a gap of 30 degrees, which is why they're being treated separately. You cannot put in cos square of 90 directly because it will lead you to a zero. That will be wrong. It's a stage process, so you do this in stages. This becomes input to this, then this creates the output here. Question number 28 is from Doppler effect. He says that the object accelerates uniformly from x to y. Its speed is increasing. So the frequency here heard will be louder, frequency here will be louder, frequency here will be smaller. He says which observer will hear the highest frequency of sound when the position of the car when this frequency is heard by the observer. So x is not possible. At y should be possible, but no. The observer, for example, the observer standing here, the observer standing here. So if we cancel x, then the car is still moving and they cross this boundary because they mentioned here. So even y will be hearing something frequency that is going to be smaller. When the car is moving towards here, the frequency will be higher, but once the car passes this, the frequency heard by y is going to be smaller. So this y cannot be possible. So we are left with z. And when will they hear this? Is this going to be when it was between x and y or between y and z? So it should be between y and z because at this point it was gaining speed, and at this section it has gained what it had to gain. So speed is already at a high rate of speed. So yeah, y to z should be d. Yeah. Because a very nice straightforward question is asking you about the stationary wave and its condition. Which one is labeled correctly? This is not an antinode, rejected. This is a node. This is an antinode, but this is not a wavelength, rejected. This is not an antinode, rejected. This is an antinode. This is node, and this is definitely a wavelength. So D will be the right answer. 32 coherent electromagnetic waves traveling in space. Because the electromagnetic wave, they are having same speed of 3 into 10 raised to the power 8 meters per second. The two waves meet at a point. The two waves have different intensities, different amplitudes. Which statement about these two waves is not correct? They have a constant phase difference at that point. If they are meeting, for example, if they had met at a point, then this is true. They have the same amplitude at that point. This is false because intensity is amplitude. As we know about waves, intensity is proportional to amplitude square. But that's not possible. So they have the same frequency. This could be correct. And if they have met at this point, that means they have undergone interference. If they have undergone interference, they are coherent, then the wavelength should be the same frequency. They travel the same speed. That is also correct because they are electromagnetic. They're moving at the same speed. So most likely, which is not correct, is going to be option B. 31 requires a bit of geometry, but let's see. He says that the D is given to you. It's a diffraction grading question, so I'm supposed to write down n lambda equals to d sine theta. The distance between the first order intensity maximum is 15 centimeters. Okay. The screen is at a distance of this. What is the wavelength of light? All right. So this is the D in this equation. And to find if it's the first two first order means that this is the lens, the grating lens, and this is our screen. This is n equal to 0. This is n equals to 1. This is also n equals to 1. So the distance between the first two orders, like this one, is 15 centimeters. And the distance from grating screen to this is 33.5 centimeters. And I believe that this information is given to you to find the angle theta. Only then you can find the lambda. So since we're dealing with the first order only, the n will be 1. Lambda is unknown. D is per meter. So this is 1 divided by 5 into 10 raised to the power 5. Sine theta requires our help. So let's find out sine theta first. Now this is the triangle that we're extracting from here. So the triangle is going to look something like this. Since this is total 15, this will become 7.5 centimeters. And this is 33.5 centimeters. This angle will be theta. Let's find out this angle. This will be theta is equal to tan inverse of 7.5 divided by 33.5. The angle, let's check the angle. Is 12.62. If you put 12.62, make sure that your calculator is in degrees. Then you calculate all the answer, and the lambda comes out as 436.9 nanometers, which is supposed to be option A. This is a good question. 32 is about filament lamp. So filament lamps have a self-heating problem. So if all the graphs are VI, then predict the behavior before you go into. So you keep on increasing the voltage. They obey Ohm's law at first, but then they don't. So their resistance increases so much that even if you pump more energy into the system, the current does not increase. They are glowing hot at this point, and the resistance is almost very high. So there should be an upward rising trend. So this fails, this passes, but this also passes. So what could be different? You see, a filament lamp, since the behavior on the other side actually suggests that if the battery was connected this way, the current going this way, or the battery was connected this way, so the current is going this way. So it could be either positive current or negative current, just the direction of the cell orientation. It should behave the same way in both directions. So most likely should be B. Here I can see that behavior on this side is different as compared to the behavior on this side. So for example, if I apply a negative voltage, it has different values of current. And if I apply positive voltage, it has different behavior for current. So the filament lamp, because it's a resistive component, should behave exactly the same in both directions. Which statement and definition about the potential difference across the component is correct? Now, I've added this part from your syllabus. You can see that it's written as the first point. Now, see the standard equation that you forget of current and voltage is I is equal to Q by T, which becomes Q equals to IT. And voltage is actually work done by charge. We forget about this. And for resistance, that is rho L over A. V equals to IR, Ohm's law, comes much later. So first you need to remember these three equations before going into the question. All right, so based on this, we have something to do with joules divided by coulombs. So energy transferred, yes. Per unit charge, yes. Not per unit time. Power transferred, no. The best answer is going to be option A. Question number 34 requires rho resistance is equal to rho L over A formula and understanding. There are two ways to do this. I'm going to choose the easier method that requires a bit of more algebra, but it guarantees that your answer is not wrong. He says that the resistance of this situation is 15 ohms, and even after all those changes, it should still be 15 ohms. So let's make the standard first. So R is equal to rho L over A. This R should be 15, given in the question. Let's accept the variables of the question, which is length, and cross-sectional area is x into x. So rho is equal to L into x squared. Let's make rho the subject to the formula. This is going to be 15 x squared divided by L. Now, since I have the resistivity of the material and we're using the same material, it says more of the same putty. So this time around, there are new parameters, but the resistance has to stay 15. So for the new situation, R equals to rho L over A. Since R is still supposed to be 15, rho can be used from previous situation, which is 15 x squared divided by L. The new situation of L is L by 2, so let's consider 0.5 L divided by cross-sectional area. And radius of the cylinder. So this should be, because it's a cylinder this time, cross-sectional area will be pi r squared. So I'm going to write down pi r squared. Notice what is being cancelled out very conveniently. So 15 cancels out, L cancels out. We want to find this R. R goes to the side, so this becomes r squared is equal to 0.5 divided by pi x squared. This x stays up. So this is r squared is equal to, this converted into half will become x squared divided by 2 pi. If you take the under root on both sides, this becomes r equals to under root of x squared divided by 2 pi. Then r is equal to x divided by under root 2 pi. So it should be B. Yeah. So I understand that you can use another method. You can use the ratio method. in which it would be rho L over A compared with another rho L over A. Sometimes I struggle with this, so I prefer this method, finding the constant that holds both sides of the system first and then do the algebra. It leads to better answers. That is in my practice, but you could have your own method, it's fine. 35 again is from your syllabus. I've added the part of syllabus where this is mentioned. This is part of memory. So the first law is about charges, and the second law is about energy. So it's going to be option C. You can find this in this part of your course. Question number 36 is a good question. This question requires a bit of understanding and manipulation of series and parallel circuits. So what's given to us is the reading of 1.5 amperes. 1.5 amperes here. Now, if I notice that how much reading should here be? You see, the current will be here, and then it gets divided. So whatever the current here is being divided here and dividing here. So if this has two identical resistors, if the resistance is doubled in a parallel circuit, then the current should be halved, because the voltage is supposed to remain the same. Yeah. So the current chooses the path of minimum resistance. So a single resistor is giving us 1.5 amps. Here, it should be 1.5 divided by 2, which is going to become 0.75 amps. Now, when I have this information, I can add these two currents together to find out how much current is actually traveling in the circuit, because I'm supposed to find the value of A2. So the current input the system is 1.5 plus 0.75, which is 2.25 amps. This is 2.25 amps here, and then 2.25 here, and then 2.25 here. So now I have to find A2. Now this is the tricky part. You see, in one branch we have 2 resistors, and the other one we have 3. I understand that this branch should have a higher current, and this branch should have a smaller current. The way we use potential divider rule is based on voltages, is based on potential differences. Here, I'm going to use the current divider rule using this simple idea that no matter what happens, since they have the same voltages across them, what should be the ratio of currents between them? See, let's call this I1, let's call this I2. So I1 should have, since it's 2R, whatever the current is going to be 1 over 2R. In I2, whatever the current is going to be divided by 3R. I2. Once you solve this, you realize that I1 is basically equal to 3 by 2 I2. And this is our conclusion, because I1 is supposed to be higher and I2 is supposed to be lower. We can see this here. Now, I1 plus I2 should be equal to 2.25. That was what we established in the beginning. Once we have this ratio, we can replace this into this equation and find I2. Once we have I2, we can find I1. Or you can simply make I2 the subject of the formula and replace it here. So this will become I1 plus 2I1 divided by 3 equals 2.25. You can take this to be 1. This is going to be 0.67. Add this into this. Take it over there. That side, divide it. Your I1 should be equal to 1.35 amps. And you can consequently find it for this one. An alternative to this is the way we do the potential divider thing. So what we assume over there is I want to find the voltage of this branch, I take the resistance of this branch. But here, if I want to find the current of this branch, then I'm going to take the resistance of the opposing branch. Is a current divider, ratio, rule, whatever. It's not a part of your course, but if you learn this, it makes things a bit easier. So this would be 3R divided by 5R. Why? 3R plus 2R into the current that is being divided is 2.25. You will find that this will also give you 1.35 as your division. So in so in your current division scenarios, you take the opposing branches. In your voltage division scenarios, you take the same branches for the potential divider. This is current divider. But anyways, it is a bit complicated, so it takes a bit of time to digest it completely. Okay, 37. For 37, I'm going to solve this question in 2 ways. You see, since it is a variable resistor, it means it can change its resistance from 0 and go up to 4 ohms. That's given in the question. I would suggest that since it is 0, when the voltage of a component is 0, the voltmeter will read 0, no energy consumption. And when it is 4, you can simply use potential divider, which is 4 divided by total resistance, which is 4 plus 6, multiplied by the EMF share, which is 6. This is going to come out as 2. Now, for example, this is the circuit that you have. You want to find the current in the circuit. Even if you do, this is going to be I equals to 1 ampere, and the voltage consumption across this is going to be V equals to IR, which is going to be 0. Because resistance 0, this component becomes 0. Now, when we come to this situation, if you want to find the current first, you want to do it with that method, this becomes V equals to I into 10. Why? Because 6 plus 4, they're in series. And this is 6 equals to I into 10. Current becomes 0.6 amps. And when you put this into here, the voltage consumption by this, V equals to IR again. Voltage consumption is 0.6 multiplied by 4, which is going to become, let's see, 6 multiplied by 0.4. Oh, it's 2.4. It should be A, but let's see. Not 3.6, but 2.4 volts. They're going to be option A. So you can use this with do this with the current method, or you can do this with the potential divider method. I would suggest do it with this. It saves time and it is more conceptual than that. Question number 38 is, in the alpha scattering experiment, the alpha beam, now notice that this question is primarily from IGCSE and O-levels. I will show you what the examiner means by this. So these are the observations and conclusions. So we understand that most of the alpha passed straight through, which told us that this empty space. A few alpha particles are deflected at small angles, which means that the nucleus or whatever is at the center is positively charged. And a very small percentage of alpha actually came back, which means that nucleus contained most of the mass of the atom. What he's done in the question is being very clever about this. He's mentioned all the observations. All the observations are given. And then based on that, we had some conclusions. Now be advised that these are actually one-to-one functions. You cannot say that if you observe that all the atoms are passing through, it is going to be the reason for mass of the nucleus. No. Whatever observation is here, the conclusion for that is very specific. If this is observation B, the conclusion is very obvious only for this one. So he's given all the answers here. Now he's going to ask you what cannot be concluded. So atom is mostly empty space. Yes, we can. Concentrated the mass of the nucleus. Yes, we can. This is point number 3. The nucleus is charged. Yes, we can. It is positively charged, but yes, we can acknowledge that. But it contains neutrons and protons. This is what we cannot know, because neutrons have no charge on them. At that stage, we only figured out that there is something at the center. In fact, we named it much later. There's something at the center that is causing the alpha particles to go away or to roll back completely. What is inside? That's something we didn't know. So going to be option C, the correct answer for this. Question number 39 again is invoking your memory. What type of decay this is? Beta positive or beta negative. So if you remember, beta positive mechanism is a proton changing to a neutron and releasing a beta positive, which is 0 plus 1. And the quark composition was up, up, down, and this was up, down, down. For beta negative, this was supposed to be a neutron decaying into a proton, P11 plus B0 minus 1. So this was up, down, down, and this become up, up, down. He's asking us that one up changes to a down quark. It only happens in this one. So it's going to be a beta positive decay, beta emitted particle positive decay, and the hadron created is a neutron. Neutron is created. It's option A. Now 40th, there are 2 ways to do this. First, let's try the logical method. He says that U 238 with 92 becomes radium, for example, 22688. How many alpha and beta minus have been decayed or have been exited from the situation? So notice that alpha is 42 and beta is 0 minus 1. So since beta cannot affect the number on the upper side, we can be very sure that we can use at least this difference to find how many alphas were rejected. So for alpha, from 238 minus 226 divided by the upper number 4, we can figure out that there were 3 alpha particles released. If there were 3 alpha particles released, then the number on the lower side, 42, if there were 3 multiplied by 2 is 6, the number on the lower side should be affected by 6. So we're starting with 92. So 92 minus 6 gives me 86. But I have 88. That means, and we understand that beta causes this number to increase. So after 86, there should be 2 beta 0 minus 1 that have made it to go 87 and then 88. That means there are 2 betas and 3 alpha particles, which is going to be option B. If this logical method doesn't sit well with you, you can always try the equation method, which is going to be U 238, 92 breaking down into RA as 2, 26, 86 with, let's say, we have X number of alphas, which is 42, and we have Y numbers of beta 0 minus 1. You can use the upper equation, upper numbers, variables, to make an equation for Y and alpha and beta, and then you can use the lower equation. But let's make the upper equation first. So this is going to be 238, arrow dealt as an equal sign. Then we have 226. Then we have X multiplied by 4. This will be 4X plus Y multiplied by 0 is going to be 0. This will get you the X. And then we can use the lower side of the equation, it's a mathematical equation, to get the value of Y, because previously we found X. We're going to do 92, arrow dealt as equal, then this is 86, then this is going to be plus 2X, and then it's going to be plus Y into minus 1. You have X from the previous part, you place it here, and then you find Y. Be careful about the negative. So again, you'll find 3 and 2. So that is all for February, March 2026, paper 1. I'll see you in the next video.